see, do we have the authors of the next paper now?
Well, he has to, he's ready to exchange.
Do we have the authors from the next paper in the audience? Oh, good. Sorry, I didn't see that. Next contribution is from Helsinki University of Technology, entitled Preparation and Characterization of Cobalt on Magnesium on Silica and Magnesium Cobalt on Silica Catalysts and Their Activity in CO hydrogenation. The authors are Niemelä and Kraus. The presentation will be given by Niemelä.
Yes, thank you. The topic of this rather conventional activity study is preparation and characterization of cobalt silica, cobalt magnesium silica, and magnesium cobalt silica catalysts and their activity in CO hydrogenation. First, I'll say a few words about the background and motivation of this study, then discuss some of the main results, and finally give out some conclusive statements. This work forms part of a larger C1 chemistry project, which started just about 2 years ago and which is funded by the Technology Development Center of Finland. The project is composed of 4 collaborating parties: Helsinki University of Joensuu, which concentrates on the development of new catalyst precursors, Helsinki University of Technology Laboratory of Physics, which studies foil model catalysts and assists in the characterization of the supported catalysts, Technical Research Center of Finland Laboratory of Chemistry, where the catalysts are screened, and finally, Helsinki University of Technology Laboratory of Industrial Chemistry, which I represent, where more detailed catalytical studies are carried out. The project is aimed at developing new industrially potential catalyst compositions for carbon monoxide activations by means of kinetic modeling. Due to this collaboration, the motivation of this study was the findings of Helsinki University of Technology Laboratory of Physics, which is represented later today by Dr. Lahtinen. The surface and ultra-high vacuum studies of partly magnesium-covered cobalt foils indicated that magnesium increases carbon monoxide adsorption, and secondly, that magnesium promotes dissociation and chain growth of cobalt foils. The aim of the present study was first of all to test the automated reactor system designed and built recently for synthesis gas reactions, and secondly, and more importantly, to determine the applicability of the previously mentioned surface and ultra-high vacuum studies to supported catalysts at true reaction conditions. Then a few words about the experimental. The catalyst support used was Grace 432 silica with a particle size distribution from 0.5 millimeter to 1 millimeter. The support was pre-treated with a 1:1 volumetric mixture of ethanol and water, dried, and impregnated thereafter with cobalt nitrate and magnesium nitrate, or with cobalt acetate and magnesium acetate, or with dicobalt octacarbonyl alone. The nitrate and acetate precursor catalysts were calcined by elevating the temperature with a rate of 3 degrees per minute to 300 degrees C for 12 hours under airflow. All of the catalysts were reduced in situ at 400 degrees C or 450 degrees C prior to the reaction. The metal contents of calcined nitrate and acetate catalysts are shown in this table. The dicobalt octacarbonyl catalyst was analyzed after the reaction. The amount of cobalt was aimed to stay constant at 5 weight% in all of these catalysts, and the molar ratio of magnesium to cobalt was either 1:2 or 2:1, which means about 1 weight% and 4 weight% of magnesium, respectively. The results stipulated in this table indicate that when magnesium was added to the catalyst, the amount of cobalt was lower than 5. Respectively, the amount of magnesium was lower than expected, either 1 or 4. These losses might be due to losses of both of these materials due during the drying stages of the catalyst, or secondly, due to erroneous sampling amounts, because magnesium oxide can react extensively with water and therefore also with humidity. The lower amount of cobalt, 3.6, is typical to the production sequence of these catalysts. And the lower amount is probably caused by either insufficient drying of the support prior to impregnation, or by a too high evaporation rate during the evaporation of the hexane solution used in the impregnation. Despite of these losses, the consecutive catalyst preparations of nitrate and acetate catalysts remained within 0.1 weight%, which means that the production sequence of these catalysts was well reproducible. Then a few words about the activity testing. The CO hydrogenations were carried out in an automated fixed-bed downflow tubular reactor at 5 bars of pressure and 235 to 290 degrees C. The gas hourly space velocity varied from 1,600 to 3,800 liters per liters of catalyst per hour. The argon to carbon monoxide to hydrogen ratio was 3:1:3 in activity studies. The temperature in the middle of the catalyst bed remained typically within 0.5 degrees C in respect to the set point value, and the steady state activity was reached after about 20 to 30 hours of reaction time. The analysis was carried out by online GC, and the response factors published earlier in literature were used for quantitative determinations. Then to our results. Generally speaking, the increase of reaction temperature increased both catalyst deactivation and conversion. It also increased carbon dioxide yields and decreased the yields of the oxygenated products. The first notable effect of Precursor was that both carbonyl and nitrate-based catalysts deactivated considerably during the reaction, whereas the activity of acetate precursor catalysts increased during the first 24 hours. This activation might have been due to the increased extent of reduction under the reaction conditions due to carbon monoxide. The steady-state CO hydrogenation activity decreased in the precursor order of carbonyl, nitrate, acetate, which is in agreement with the previous studies. This decrease of activity was directly related to the extent of reduction, as observed by XPS and thermoscale under reductive atmosphere. The probability of chain growth was quite similar with nitrate and carbonyl catalysts, whereas it was clearly lower with acetate precursor catalysts. This is also at least partly due to the different extent of reduction, though the probability of chain growth is also a function of dispersion, which is not known in this case. All of these catalysts produced small amounts of oxygenated compounds, which might be due to retained impurities of the silica matrix. The yields were significantly higher with carbonyl and acetate catalysts, around 9 mol%, and clearly lower with nitrate catalysts. Though higher pressures and lower hydrogen to carbon monoxide feed ratios would probably have improved the oxygenated yields of our catalysts. Then to our main emphasis, namely the magnesium promotion. A clear effect of magnesium promotion were the lower extents of reduction. When we are talking about nitrate precursor catalyst, the plain cobalt catalyst had a reduction extent of 66, and with magnesium promotion it went to 40 to 19. The same effect was still observed also at the reduction temperatures 450 degrees C. The amounts observed with the thermogravimetric analysis are not accurate, and they have been determined according to the reduction sequence of cobalt-3 oxide 4 to cobalt oxide to metallic cobalt. With acetate catalysts, the effect of magnesium was not so visible because acetate catalysts were very badly reducible throughout. The magnesium cobalt ratios stipulated in this table have been derived from XPS spectra. These results show that when magnesium is impregnated after cobalt, it at least partly covers the active cobalt on the surface, and vice versa. Some of you might be interested on the actual spectra. Therefore, first we'll have a look at the XPS results of nitrate precursor catalysts. The first line, represented by air, shows the nitrate catalyst after calcination, and the spectrum fits well to cobalt 3 oxide 4. Line A shows this spectrum of this catalyst after reduction, and the location of metallic cobalt is indicated by red lines. It shows that the reduction has been effective. Line B shows the spectrum of magnesium cobalt silica, and the cobalt signal has been considerably decreased due to magnesium coverage. Cobalt magnesium silica, represented by line C, gives a strobel cobalt signal with some of the metallic species on the surface. The XPS spectra of acetate precursor catalyst is quite different. First of all, the spectrum of calcined catalyst could not be fitted to cobalt 3 oxide 4, and therefore we decided to determine the XPS spectrum of the precursor prior to calcination. And in fact, the precursor and calcined catalyst, the spectra, they represent each other. And there's no significant change in the spectrum, even when we are talking about reduced catalyst or magnesium-promoted catalysts. This is also in agreement with some of the previous findings. The effect of magnesium promotion on nitrate precursor catalysts depended on the impregnation order. When magnesium was impregnated after cobalt, the activity of the catalyst dropped quite clearly, from 43 to 30. When cobalt again was impregnated after magnesium, the activity either remained at the same level with the unpromoted catalysts or even increased. This is quite clearly in agreement with the previously shown XPS results, and therefore this lowering of the activity of magnesium cobalt silica was caused by the blockage of the active cobalt sites by magnesium oxide. For acetate precursor catalysts, the only effect of magnesium was the loss of activity, irrespective of the impregnation order. A facile explanation to indifferent impregnation order is the highly dispersed bonding of the acetate salts with the oxygen of the silica matrix, as has been suggested by Matsusaki and co-workers. In fact, the present SIMS results showed that with acetate precursors, both cobalt and magnesium were evenly distributed within the silica matrix, whereas these species were concentrated on the outer surface of silica with nitrate precursors. Also, XRD could not determine the crystalline size of acetate precursor catalysts. Another very clear effect of magnesium promotion was the decreased carbon dioxide yields. Recently, Gopal and co-workers have observed that magnesium oxide facilitates the formation of formate species by the reaction of carbon monoxide and water. These formate species, generated on magnesium-promoted catalysts, could be subsequently hydrogenated to methanol, rather than carbon monoxide and water simply being converted to carbon dioxide via the water-gas shift reaction. The variations in the methanol yields in our experiments were, however, too small for conclusive statements. Magnesium promotion had no significant effect on the product distributions of our supported catalysts, as can be seen by the almost constant values of alpha and by almost the same amounts of oxygenated products with both nitrate and acetate precursor catalysts. In contradiction to these results, a slight increase in the formation of C2 oxygenates has previously been detected, though at higher pressures of 21 bars. Also, some changes in the product distribution due to magnesium deposition on cobalt foil model catalysts were observed, namely a small but detectable shift towards higher molecular weight hydrocarbons. This increase in the chain growth on the model catalysts could be due to the increased propensity of carbon monoxide dissociation in the presence of metallic magnesium. On supported catalysts, magnesium is present as magnesium oxide, and magnesium oxide does not promote carbon monoxide dissociation even on cobalt foils, and therefore the chain growth enhancement was not visible on our supported catalysts. Previously on my speech, we had a look at the effect of reduction temperature to the extent of reduction. And since the reduction temperature did have a notable effect on the extent of reduction, it was interesting to study the effect of in situ reduction on the activity of our catalysts. Interesting enough, higher reduction temperature resulted in lower activity of both plain and promoted cobalt nitrate and cobalt acetate catalysts. The loss of activity was considerably smaller with promoted catalysts, as can be seen from these figures. With plain cobalt, the loss of the activity fell to about half of its original value, from 21 to 19 with nitrate precursor catalysts and from 17 to 11 with acetate catalysts. Whereas this loss of activity was only slight with both nitrate and acetate catalysts when they were promoted with magnesium. Apparently, the slightly higher degree of reduction was accompanied with agglomeration, and these results suggest that magnesium hindered this agglomeration, that it functioned more or less as a structural promoter, retaining the active surface area, as suggested already in some earlier studies. Finally, a few words about the deactivation and reaction rate equations, though they are of preliminary nature. They were derived only for cobalt nitrate catalysts at temperatures of 235 to 290 degrees C. They are of preliminary nature due to experimental limitations. Namely, at the lower limit of 235, the conversions were very low, and the analysis accuracy was not good enough. On the other hand, at the higher limit of 290, the reactor was not isothermal anymore, and the mass transfer limitations can affect the reaction rate at high conversions. The deactivation equation shown over here was used to correct for the deactivation during the reaction rate determinations. Even though the deactivation equation was derived at constant partial pressures of carbon monoxide and hydrogen, its use improved the fit of the reaction rate equation to the experimental data. Despite of the previously mentioned experimental limitations, the activation energy of 128 kilojoules per mole and the reaction rate orders of approximately 1 in respect to hydrogen and approximately minus 0.9 in respect to carbon monoxide are well in agreement with the equations previously determined for supported catalysts. To conclude, the effect of precursor was quite well in agreement with the previous studies. The activity of the catalysts decreased in the precursor order of carbonyl to nitrate to acetate, and more of alcohols were produced with carbonyl and acetate-based catalysts compared with those of nitrate. The probability of chain growth was approximately the same with nitrate precursor catalysts and carbonyl catalysts, whereas it was clearly lower with acetate catalysts. Because these results are well in agreement with the previous studies, it shows that the reactor system operated well, which was one of our reasons of doing this study. What comes to the effect of magnesium promotion, it decreased the extent of reduction, it decreased the activity and carbon dioxide yields. The promotion effects of surface and ultra-high vacuum studies were different of those of the supported catalysts. Furthermore, it was obvious that the effects of Precursor were stronger than those of Magnesium Promotion, and therefore our next emphasis is to determine more closely that what are the reasons behind these differences in the precursors. In the end, I would like to acknowledge the financial support of Technology Development Centre of Finland and the Helsinki University of Technology Analysis Centre for assistance in the catalyst characterizations and the experimental assistance of Mr. Juha Järvi. Thank you for your attention.
This presentation is now open for questions. Another short question from Professor Barthelme.
Try. In some work by Johnson and myself, we found that the activity of cobalt catalysts increased with extent of reduction. We also found that carbonyl precursors resulted in higher extents of reduction.
Yeah.
Could that explain the higher activity that you observed for your cobalt carbonyls?
Yeah, it does.
Yeah.
It does.
Yeah, and in terms of these precursors, something you might think about is the preparation of the support as well, and the role of hydroxyl groups in oxidizing the cobalt.
Yeah, yeah. Actually, that is one reason why we thought that first of all we lose some of that carbonyl from the support, that the pre-treatment temperature is not high enough, that there's still some active hydroxyl groups, and therefore we don't have that 5 weight percent.
What's the purpose of the argon in your feed gas?
Well, argon has been used as an internal standard when we are determining the product distributions, and it can also be used as a diluent to the feed gas.
It doesn't affect your catalyst performance,
Actually, I haven't been.
kinetics and so forth?
Actually, I haven't been running the system without argon. To be sure of that, I should try it. But it doesn't react under those conditions, definitely.
Are there any other questions? Thank you once again. We're very interested.